There's only one thing to do with rotten windows. You don't need to be subtle with rotten wood. But what do we use for a replacement? Let's start by asking what window frames have to do. First thing, they have to support the glass and keep out the weather, wind and rain. And wood rots, even if you paint it. So, what could we use instead? Well, we could use iron, but iron rusts, and it doesn't take long about it. But here's aluminium that's been in the cold and wet for weeks. Both metals, but they don't react in the same way. Why not? Let's take a closer look at iron. Exposed to air, iron corrodes. Oxygen reacts with the iron to form iron-3 oxide. Rust, and rust is flaky. Water and oxygen can penetrate it, producing more rust. But what about aluminium? Doesn't it react with oxygen? Yes, it does, but you have to look much more closely to see the corrosion. This electron micrograph is magnified 250,000 times. Aluminium reacts with oxygen to produce aluminium oxide in this very thin layer. Why so thin? Because the oxide is airtight, so aluminium doesn't get eaten away, and we could use it for a window frame. But a window frame has to be strong as well. So how strong's aluminium? Well, we can test it. Not bad, 21,000 newtons. That's the same as a mass of over 2 tons. So how does that compare with steel? Steel's almost twice as strong. But as well as corroding, steel is also dense. That might not seem important until you're doing this all day. So, aluminium is a good choice for replacement window frames. But what makes one metal less dense than another? You know what metals are made of? Millions of atoms identical to each other. Like these metal balls, they're packed together. But there are different ways of packing identical spheres. And the way they're packed determines the density of the metal. This way of arranging the atoms means they aren't as tightly packed as these, and they can be packed even closer together. Now, if the atoms all weighed the same, which arrangement would have the highest density? This one? Or this one? Or this one? Of course, it isn't quite that simple. The atoms of different metals have different sizes and masses, but packing obviously has some effect. Try it if you don't believe me. So now we know why aluminium is likely to have a low density, and we already know that it's fairly strong and doesn't corrode. Sounds pretty good. So why not get rid of all the iron and steel and use aluminium for everything? Well, after the war, people tried, literally. Whole houses were made from aluminium.
It's an aluminium house. Everything ultra-modern, it has one old-fashioned drawback. When you kick it, it gives out a rather embarrassing sound.
But one other thing you should know about aluminium, it's not cheap. Remember why? So why was there suddenly so much of the stuff around? Let's take a look at the production curve. Before 1936, aluminium was only produced in small quantities, but strong, non-corroding, low density, it makes very good aircraft, and thousands of them were needed during the Second World War. But who needs warplanes in peacetime? The search for alternative uses was on, and it has been ever since. Back in the 40s, they tried everything. Houses, baths, cupboards. Imagine living in an aluminium house.
A deck chair has nothing on these houses when it comes to...
There aren't many left. So what was the drawback? Have you ever touched an aluminium window frame at night? Certainly cold. After all, metals are all good conductors of heat, but possibly wet as well.
So far, only a few metal houses have come to Britain. When there are more of them, more of us will be able to find out what it feels like to be permanently canned.
So, metal houses weren't a great success. But there is one important object in our lives that is almost entirely made out of metal. The automobile industry worldwide uses 10 million tons of steel every year. Different parts of the car, different properties of the metal. So what's so good about steel? Know what these are? Parts of an axle. First you have to melt the steel and cast it into roughly the right shape. But there's more shaping to do to finish the axle. Blacksmiths have been doing this to steel for centuries, but the steel has to be very hot without it melting again. That's one useful property of steel, and some other metals. Some metals become more brittle when they're hammered, but not steel. There's a special name for this property. Strange, but treating steel like this actually makes it stronger. $20 million cars, 40 million axles. That's one property of metals. And iron and steel in particular, that's easy to forget. But do metals have to be hot to be reformed? Apparently not. Looks like thin steel can be pressed into any shape, but it has to be strong. Nobody wants to drive around in a car that would crumple. Steel is strong from whichever direction the force is applied. Strong when it's stretched, and when it's squeezed. Steel has to be all these things just to make the body of the car. But if you want the lights of the instruments to work, you'll need another property. and probably some other metals. Is there an alternative to metal cars? Well, yes, some cars have plastic bodies. But what about the engine? Remember, there are repeated explosions going on in there. Like most metal, if you polish steel, it'll shine. A property not to be underestimated. But normally we cover it up, despite the attempts to make cars from stainless steel. But out in the open road, you want to feel safe. We think of metals as strong. But what is strength? And how do we measure it? It's obviously important to know how strong metals are, but there has to be a more scientific way of measuring strength than this. Ah, that looks more convincing. We've seen there's more than one type of strength. Here the metal is being tested to see how it behaves when it is pulled. The force pulling the metal strip is increased until eventually it reaches breaking point. This is a turbo model testing machine. The whole process is computer controlled, continually measuring the force on the metal and the stretching it produces. So how do different metals behave? Let's take a piece of steel like that used in making a car. Now knowing what force will break it is one thing, but knowing how it behaves before it breaks might be more important. At first, the force goes up rapidly. The steel doesn't stretch much. Then suddenly, the metal stretches and it breaks. Now, let's take a piece of aluminium. What's the difference? Curves of a similar shape, but one breaks more easily than the other. So which would you make cables to support a suspension bridge out of? Or a car? Take another look at steel. Do all metals behave in the same way? And are they as strong when they're compressed? The only way to find out is to try it. Different metals, different properties. So what's going on when a metal stretches and breaks? Let's take a closer look. Before breaking, the metal starts to stretch and thin out. Let's go back to our model of metal atoms. As we pull on the end of the bar, look what happens to the individual atoms. They slide past each other as the metal is stretched. If the atoms slide past each other easily, the metal stretches easily. It is ductile. But in hard metals, sliding is more difficult, so the metal snaps. Remember the different ways metal atoms can be packed? We've already seen how this affects the density of different metals. But what about the other properties? How are they affected by packing? This is how the atoms of sodium are packed. Closely or loosely? Well, pretty loosely. It's called a body-centered lattice. You can see why. Loosely packed atoms, a dense metal or not. In fact, it's less dense than water. But if the atoms aren't packed tightly together, how hard is a piece of sodium? Now, atoms of aluminium are more closely packed. See, not so much space between the individual atoms. Aluminium doesn't float, so you know it's denser than sodium. But if the atoms are more closely packed, would you expect it to be harder or softer? How close can atoms get? See these hexagonal patterns? This is the closest form of packing. It's titanium, pretty rare stuff. With atoms packed this tightly, what properties would you expect? Harder or softer than aluminium? And other properties? Well, think about the various forms of packing and the distance between the atoms. How might that affect the melting point of the various metals? Right, here's a practical question. What's these racing bikes made from then? Well, you want them to be light and strong. Aluminium by the sound of it, and tubular aluminium at that. But this bike's different. Built from a metal of even lower density. Now, which metal could that be? The frame is cast from solid magnesium, less dense than aluminium, and because it's solid metal, even stronger. In conditions like these, any weight saving could make a winning advantage. So, why isn't everyone doing it? But magnesium's an exception. One metal, simple solution. But take something complicated, like an aeroplane. Different parts of the plane, different metal properties. Each part subjected to different forces, but all the time a continual search to make each element as light as possible. Which metals does that suggest? Come to think of it, let's ask a different question. How many pure metals have you seen in this program? Pure metals almost never offer the properties we need. So what do? Mix metals of different properties. Brass looks like a metal, but it's a mixture of zinc and copper. Here's how copper behaves when it's stretched. It's ductile, easy to work, but soft. And here's zinc, brittle and not that hard. So how does brass behave? Like this, much stronger than either. Mixing metals gives us more useful properties. Metal mixtures like this are called alloys. But how are the atoms arranged? In the same pattern as pure copper. But the zinc atoms are slightly larger. Different size atoms make sliding past each other more difficult. So brass is harder than pure copper or zinc. New alloys are being made all the time, particularly in the aircraft industry. A search for the ultimate combination of lightness and strength. Why? Because saving weight in saving fuel. But couldn't we do without these metal mixtures? Maybe, once upon a time. But try taking all the alloys out of a modern aeroplane.